Alright, sorry this wasn't up yesterday. Turns out I wasn't just sitting around the house with Barrett. Ended up having to take him to the doctor because he's getting sick and a bunch of other exciting events. So here it is today. So he's not helping me because he's sleeping because he doesn't feel good. So I'm gonna just kind of recap. Last couple of days in class, we've just been talking about graphs and concavity and slopes and extrema and all that good stuff. So just kind of recap all that before I give you the problems. So this might end up taking a while. Oh, and I'm going to do a couple more examples because you haven't really seen stuff like this yet. So just in general, if you haven't realized yet, the whole section is about this derivative and the second derivative and then how those graphs or how ideas we can use from these connect to the graph of an original function. So basically what's been going on is you could either be given a graph of a function and you're going to be asked questions about the derivative and the second derivative. You may have to draw them, or you may just have to answer questions about them. It's always the same types of questions. It has to do with extremas and concavity. But then you can also be given functions and ask those same questions. So I'm going to do just examples of each here. What to do if you're given a graph, how to proceed depending on what you're asked, and then what to do if you're given a function. To start, I just have this weird thing drawn right here. If you're ever given the graph of an original function and asked questions about extrema or slopes or concavity, this should be the easiest thing ever. You probably won't see that on an AP test because it's too easy. Because all your information's right here. I mean, if you want to talk about slope, like where's the slope positive, you're just, it's going up from left to right there. So I don't know, maybe this will help just to look at it. Let's say you're talking about slopes and your extrema. Here's your thing you guys always make. If you're talking about the derivative, the slope would be positive right there, and then it would turn to negative to right there, and then you had a positive slope again to right there-ish. Right, I'm lining it up. I guess I didn't line it up very well. Imagine, there we go. There now, it looks like it lines up. And then we get negative, positive, negative. So that would be like your slopes. And so if you were asked for extrema of this, you could do it without looking at the graph. When the slope changes from positive to negative, you got maxes. Negative to positive, you got mins. Right? And that's easy to see looking at the original. And you can also look at concavity. It doesn't line up with this. It's not slopes. Slopes are just increasing and decreasing. Concavity, remember, is how the slope is changing. So if you're looking at the graph of the original, you're looking for things that look like parabolas, right? Because around things that look like parabolas, like this one is going to be concave down, because if my pencil is the slope, it's getting smaller and smaller and smaller and smaller until right here. Hopefully you can start to recognize how to see points of inflection on original graphs. This is like an upside down parabola, and then it switches to a right side up parabola. So if you were doing second derivative, right from there to there, that's concave down. So you would know your second derivative, that would be negative. Right? It doesn't line up with these. From there to somewhere right in here, now that's concave up, and then it changes to down again, and this thing's just going to change back and forth. I just wanted to help you see where these things happen. That would be down, upside down parabola, and then it switches to a right side up parabola. So it's points of inflection are usually in between upside down and right side up, little parabola looking thing. I don't like using the word parabola because they're technically not parabolas, but that's kind of the general idea. up, then that would be down, and then somewhere right in between those ones, it'd be up again. So looking at an original function, it's really easy to get concaves, ups and downs, points of inflections, just looking between the parabolas. Extreme values are really easy if you're looking at the original. It's pretty easy stuff. But all this, I almost mentioned all of that in this one picture. On page 217, there's a good little table, because these are the kinds of things you should have in the back of your mind as you do all of these problems. It kind of connects the graph with the words. The top left one, differentiable, is just, remember the ability to take the derivative. This is smooth, there's no corner, so I could do the derivative of this anywhere. But yeah, it says it might rise or fall, it doesn't matter. This just says a slope, a positive slope. It could be squiggly, it doesn't have to be a straight line. It doesn't have to be a nice curve. It could be wavy. This just means the slope is always positive. That's all that says. You can still have concave up sections and concave down sections, which this does, but the slope is continuously positive through that whole thing. Same thing here, just slope is continuously negative through that whole thing. Concave up and down, this is where you get your parabola looking shapes. Could go this way. Could have a positive slope and be concave up, or it could have a negative slope and be concave up. Same thing for down. Could have a positive slope and be concave down. Could have a negative slope and be concave down. But it can't be wavy, because waviness would be changes in concavity. Inflection points, you can imagine they're right here. It's like where the parabola changes from one to the other. Do the pencil thing. Hey, my slope's getting bigger. Hey, my slope's getting smaller. Right? I'm just going through all these. We know local maxes and mins pretty good, where the derivative changes sign. Here's one that you may not have thought about. I don't think we've talked about yet. If the derivative is 0 and it's concave down, that's a local max. That's one way to check for an extrema without plugging in numbers to the derivative. Like before, we'd always get our derivative function, figure out where it was 0, and then plug in a number on the left, plug in a number on the right, and use the sign of the derivative to give us maxes and mins. You could also figure out where the derivative is 0, and then take the second derivative and figure out the sign of that. Because if it's concave down, obviously it's going to be like this. And if the slope is 0 at that point, it's going to be a max. And if you have a concave up section with a slope of 0 in it somewhere, you're going to have a min. Okay. So, putting all that together, I'm just going to do a couple examples now. First one, you're going to have the graph. Here's the graph of a derivative, and we're going to draw the graph of the original. Whenever you do this, any of these graphing, or even not graphing, just looking at functions and answering questions about first and second derivatives, no matter whether you're given the original first derivative or second derivative and finding pieces of all of the other ones, there's basically two main things, or especially if you're drawing, there's two main things you need to keep in the back of your mind that you need to find. The extreme values and the concavity, because if you can figure out intervals for these, well, if you can figure out the intervals for this and find these, you'll know pretty much everything you need to draw the picture if you need to, or answer all the questions. Because when you find extrema, you're finding they occur at endpoints, right? So you'll find endpoints. The big thing extrema tells you is the slopes, right? Because you figure out where the slope is 0, and then you figure out if it's positive or negative to the left and right, so you find all your hills and valleys. So that'll tell you, if the original is increasing or decreasing. And then this also helps you find corners, or, right, because that's where the derivative can't be taken, or there could be vertical places in the graph like that that would be a place where the derivative can't be taken, right? That's where the derivative does not exist. So by finding extrema, you're figuring out all these things anyway. So then you also got to think about concavity, because this tells you a lot about slopes. This will tell you a lot about whether it's curving up or curving down. And that pretty much tells you everything about you need to know about the graph, right? Okay, so this one. It's an example out of your book. I traced it. I don't remember what page it was on. It's like example 8 or 9 or something like that. In the same section. So if you've got that and you want to draw the original. I tried to make my x values line up because sometimes it's easier. But you may not want to play along at home on this one. It might be best just to watch, because if you want to pause it and copy that all down, go ahead. But anyway, I don't know what you want to do. So you've never seen a piecewise derivative. Well, that's what's different about this one. We've been doing lots of these in class, though, that, look like that. So you could probably do that section. Remember, first thing you got to realize is, what am I looking at? And in this case, you're looking at the derivative. Keep that in the back of your mind, or actually in the front, because as you saw yesterday, even sometimes I forget what I'm looking at, and I did that one problem wrong because I thought I was looking at the original. So, good thing to have there. So we're looking at the derivative, which, remember, tells us all the values of the slopes for the original. So we can go through and we can draw this. Actually, on this one, part A says to find the x-coordinates of all the local extrema and points of inflection. Well, that's good, because that'll help us draw this. We could sit here and go through without finding those and just kind of, I don't know, because I think in my head I kind of do that anyway. So it's good the question asked, because remember the two things I said to find? Well, that's what part A asked. It asked for the x-coordinates of all the local extrema and all the points of inflection. That has to do with concavity. So let's just, I didn't really leave myself room here. So the extrema, let's do that one first. So you have to remember where extreme values occur, obviously, to be able to do this. And it's those three things we keep repeating. It's either endpoints, hills and valleys, or corners where the slope does not exist. So looking at this, let's just focus on this right now from here to here. Our endpoints, I guess we can do those. There's an endpoint. It's supposed to line up with -4 there. Didn't really do a good job. There's -4. So x equals -4 is probably an extrema, because we have an endpoint, and to the right of that endpoint, let's see, the slope is positive, right? I don't care what the value really is, I just know, remember, these are my slopes. So here, the graph of the original function, to the right of that endpoint will have a positive slope. So, I mean, that means, okay, here's my right endpoint, to the right of it will be a positive slope, so that's going to be a local min. I don't know why I keep switching. I told you we're just gonna focus on this right now, so we'll worry about this later. It's also, remember, hills and valleys, but don't go right here and be like, oh look, a local min, because then you would be thinking of the original. Think about slopes, because that's what we're looking at, is slopes. Remember, hills and valleys occur where the slope changes sign. Oh, hey, we're looking at slopes. Where does the slope change sign? Right here it changes from positive to negative, right? So at x equals -3, my slope is going to change from positive to negative. So that's going to be a local max. And then at here, we got a sign change again from negative to positive. So from negative to positive slope, so x equals -1 will be a local min. And then we're going to come up here and we're going to deal with that in a minute. So there's my extrema just for this part. We'll worry about the rest in a minute. And then concavity. Remember, concavity is all about how the slope is changing. So if you're looking at the original, it's the parabola effect. If you're looking at the second derivative, it's greater than 0 is up, less than 0 is down. No, you might be like, well, we're not looking at the original or the second derivative. We're looking at the first derivative. Well, that's okay. We can figure it out. Remember that I'm trying to pause. I'm trying to go slow. I don't know if it's helping. The second derivative greater than 0. So looking at this, where are you going to see that happen? Remember, second derivative is kind of like the slope of the slope graph. So you can just think of it as, or you can think of, I remember the best way to explain it, concavity. If it's concave up, the slope is increasing, right? The original. Concave up, concave down, the slope is decreasing. So we can just write, so if y prime is increasing, because that's our slope, that's concave up. If y prime is decreasing, it's concave down. So we got y prime here increasing, it's going to be concave up, decreasing, it's going to be concave down. So whenever I change, that'll be a point of inflection, right? So here's my derivative. It's decreasing until right here, and now it's increasing. So that tells me x equals -2 will be a point of inflection. And that's all we're going to worry about right there. So let's go ahead and get this part graphed. And I don't think, no, on this one they didn't give you any conditions. So when you start to plot these points, x equals -4 is a local min. You don't know how far up or down to go because they're not given to you. On one of your homework problems, it tells you, like, okay, you know all this stuff, and you know f of -4 equals -1. So, like, if this was given, you would go here to -4, -1, that would be your point. You'd put all the, probably, some of them, I'll do that, I'll do another example later, but they give you more than one point, so they're like, x of -2 is this, and so I'd go through and put all those points on the graph, and then use these ideas to fill in the dots. But since we don't have any of those, I know that's a local min. I know at -3 I'm going to have a local max, so I don't know, I'll just come here somewhere. I just completely random that I put it at 1. You could have put it up here, it doesn't matter, because I'm not told anything. It's just a possible graph. X equals -1 local min, so I could put it down here, I could put it down here. I could even put it up here if I really wanted. Have this come up, and no, that'd make it, I don't know, I'm just being stupid. I'll put it down here just for fun. And then at -2 we have a point of inflection. So I'm going to change from concave, looks like this is negative, so the slope is decreasing, so I'm going to be concave down, and at -2 I'm going to switch to concave up. So also I'll just go from right now, start at -4, and I know I need to be concave down until I hit -2. So I'm just going to go upside down parabola until I hit -2. Boom, right there. Now I need to be concave up. Well, this point isn't going to work then. It's okay. These are hard to do. I should have done it in pencil so that I could erase it and bring it up here. Because I'm concave down, I need to switch to concave up. I guess I can kind of, I don't know, that'll look weird. I'm just saying I don't think my picture will look right if I come down that low. So I'm just going to be like, whoosh, there. That way there. That's a point of inflection right there. And now I'm coming back up. Oh, okay. I was like, I forgot one part. Ignore that. One thing that could have helped to actually pay attention to these values, it'll help guide your drawing. For example, this is my derivative. So my slope, like, is 1 right here, which I look a little too steep to be a slope of 1. I should be more like that. But here's where we get to this part, this endpoint, or this hole in the graph. If you got a hole in a derivative graph, that means your original wasn't differentiable at that point. So we come up here and we get to 1.5. So that just means my original graph is going to be coming up, and I'm not going to be necessarily at y equals 1.5, but I'll have a slope of 1.5 right there. So imagine a slope of 1 is probably like this, so I'm a little steeper. So there's about a slope of 1.5. And then what's going to happen? Well, you see this jump from 1.5 down to -1. So if you've got an open hole in the slope, remember these are the values of the slopes. In order for it to just jump like that, from 1.5 to all of a sudden -1, you're going to have a corner, a sharp corner. So my slope goes from 1.5, right? I'm curving up. My slope's at 1.5. All of a sudden, boom, it jumps down to -1. That'll give us a sharp corner right there. Now we can go through. Now we'll go through and do these, and that ends up actually being a local max. Because the slope has that gap where it doesn't exist. Remember, extrema could occur at, well, we said corners, but corners occur where the slope does not exist. So here's another point where the slope does not exist. X equals 2. Slope jumps from +1 to -2. So it's going to jump from +1 to -2. That's going to be a local max also. And then the rest of it, it's all defined. So that's how you deal with gaps. Just look at what the slope, from here, the slope changed from positive to negative. So that's how we knew that one was a local max without drawing it. Then we're going to change from positive to negative again. So coming along here, let's see, I got all my, I don't want to put the points on yet, because as you can see, sometimes you miss them. So I got a corner, then what happens? Coming along, I have a negative slope. At 1, I change to a positive slope. So, what's that? I think oh, jeez. This is going to get crazy. Changing from a negative slope to a positive slope. Hopefully some of you are ahead of me. I'm a little slow. If you change from negative slope to positive slope, you're going to have another local min. Alright, so our thing is going to come down, and at -1, I'm going to turn around so I can go, I should have made that steeper. Something like that. There's a local min right there, because I changed from negative slope to positive slope. Now I'm going to have a positive slope till I hit 2, and then boom, jump down to a negative slope again, and now my slope will just stay constantly -2 until there. So that was rough. So that's how mine ended up looking. The one in the book. Remember, it doesn't matter where you start. Remember, I just randomly started over here, but they have the same thing: a curve and a couple corners where those slopes don't exist, and then a straight. This would be a straight line because the slope is constantly -2, so you'd have a slope of -2. So that's how you stumble through those. And you could answer lots of questions about those, but as long as you have all that stuff in the back in your mind, hopefully you're seeing how it all fits together, because it's impossible to come up with every question to every situation. I mean, it would take us forever. Like, okay, now we're going to answer when is the original increasing or decreasing. Like, yeah. Anyway, next problem. What are we going to do next? This will hopefully go faster. Oh yeah, now do one without the graph. So here's the function for the derivative. And we're going to graph the original without seeing the graph of that. So you might think, that's hard, but it's really kind of the same as we just did, except we don't have a picture. Again, two things we're going to focus on is our extrema and our concavity. If we can do those two things, we can get a good picture of our original. So let's do extrema first. I hate that word. I don't even like saying that. I'd rather just say maxes and mins. This just sounds stupid. Okay. Remember, this occur when the slope changes sign. So remember, like, if you've done lots of these where you would find the derivative, take the derivative, set it equal to 0. To figure out where the slopes are 0. Also figure out where this does not exist, which in this one it always exists. And then you'd find endpoints, but this won't have any endpoints. So all we need to know is when the slope equals 0. So we got to solve that. So we can factor for, is that 4x squared? Wow. And then you'll have x minus 3 equal to 0. Set each factor equal to 0. So 4x squared equals 0, x equals 0, x minus 3 equals 0, x equals 3. So there's our two critical points. So that's 0 and 3. Plug in, right, you've done lots of these. Plug in -1, you get -4 minus 12, that's going to be negative. Plug in 1, you're going to get 4 minus 12, negative again. Plug in 4, 64 big, minus, I'm just doing it in my head. I think it's going to be positive. You can confirm it with a calculator, right? You just plug it in numbers. Oh, you don't have calculators. That sucks. So, work it out. Okay, so now we got negative, negative again, and then positive. So there we got a local min at x equals 3. Right? Well, this sign chart's going to really help us. Like, we're already kind of drawing the graph, right? My original is going to be decreasing from negative infinity to 0. Then I'm going to have a slope of 0, so I'll probably have a flat spot. Then decreasing again, and then it's going to increase over here. But not with corners, obviously, because if I had to have oops. Okay, I was saying, I accidentally shut the camera off. There's not going to be corners, obviously, because if there were corners, that would have, we would have gotten not exist. These are going to be smooth curves, because that's where the slope is 0. Because that's how we figured this out. So all we've got is a local min at x equals 3. Pretty good picture of our graph here, but we need to know about concavity, because just because we have a negative slope doesn't, I mean, it's not necessarily going to be a straight line. It's probably going to be like curved down like this, or it could be down like this. So concavity tells us, is this thing going like this, or is it going, that's negative slope concave up, but you can also have negative slope concave down. So one of those two things is happening right here. I'm guessing it's going to be this one, just because then it'll flatten out, but we'll see. And we'll find concavity by looking at the second derivative. That's what we got to do. There's our first derivative. I think you can even make yourself a little, do it in a different color. so you don't get mixed up between the two. Extrema, you use that. Concavity, use the second derivative. It's going to be 12x squared minus 24x. There's set that equal to 0. Basically now you're just doing the same thing as up here, but you're using second derivative, so it's going to tell you concavity. So 12x squared minus 24x equals 0. Factor. So that x equals 0 and x equals 2. Make yourself a little sign chart for concavity. Just don't get confused between this one and this one. They're telling you different things. 0, 2. Just like over here, we did the same thing, but for different ideas. This told us slopes up or down. This told us concavity. Concave down, concave up. Alright, doing the same thing back here. To the left of 0, if I plug in -1 here, let's see, that'd be positive 12 plus 24, so that's going to be positive. Plug in 1, that'd be 12 minus 24, that's going to be negative. And then plug in 3, so that'd be 9, about 100 minus a smaller number, it's going to be positive again. So that's our concavity. That just tells us here to here it's concave up. Right, then it's going to switch to concave down. I shouldn't have done that so abruptly. Right, concavity switches like in between parabolas, so you can still go like that, and then so it's going to be something like that. So if we were asked for points of inflection, we got 2. We got 0 and 2. I don't know if we were at. I don't remember. If the question asked that, cool. Now let's sketch the possible graph. So we're going to take all this information and put it together for us. It says possible graph again because you don't have any for sure y values for your original x's. So it doesn't matter where we start. Let's see. Where are my key points? At 0, I got a flat spot. Okay, at 3, I got a local min. I'm just figuring out how far to go here. 0 and 2. This looks like I don't need much more than this. Okay, local, start here, maybe that'd be easy. Local min at x equals 3. When I think of min, I think low, so I'm going to put it down here. You could even put it up here, it doesn't matter, but I think small. So I'm going to put a local min here, and to the right of 3, well, isn't it always going to be concave up? It's going to have a positive slope and be concave up. So it's just going to be like something like that. Now I'll go to the left of 3. Remember, I just started here randomly. You could have started on the left if you want. I just knew that was a critical point. Local min, easy place to start. To the left of 3, what do I got going? I got a negative slope, so it's going to be coming down like that. And, I'm going to switch concavity at 2. So I'm going to be concave up with a negative slope until I hit 2. So there's a good, negative slope with concave up. Right? Now I'm going to switch to concave down. Still with a negative slope though. So I still got to be going down, but now instead of like an upward shaped parabola section, I'm going to have a downward shaped parabola section with a negative slope until 0. So I'll put it up here because that'll be easy to draw. Boom. Negative slope, concave down, negative slope, concave up. Concavity changes and slope changes. Oh, nope, my concavity changed over here. That was stupid. I don't know why I said that. This is the longest video of life. And what's up over here at 0? What do we have? A point of inflection. So now I was concave down and I'm going to change to concave up. And remember we had a flat spot too. Oh good, I got a flat spot. And I'm going to change to concave up with a negative slope. So concave up, that, right, negative slope. There, good. Flat spot. There. There it is. Answered all the questions I needed to. There's a possible graph. concave up, yep, till 0, and then from 0 to 2, 0 to 2 is concave down, from 2 on is concave up. Check up here, negative slope all the way, negative, 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 changing to positive at 3, changing to positive to 3. This is going to be one of those things where it looks easy. Maybe it doesn't even look easy, I'm making it look hard. So when it looks hard, and then it is hard. That's fun. One more. Maybe not. Oh no, I already did that. So in your homework, first one's just going to be similar to the one we did before. Really, you don't need the second derivative. You can look at the first derivative and probably draw your graph. And, 46 and 47 are going to be they're going to give you word problems, and it's just going to say sketch a curve. It has to go through the origin, has to be concave down when x is negative, and concave up when x is positive. So there's a lot of possible pictures you could do. You just got to make sure it fits these conditions. And then 47 is the one I was talking about where, okay, they're going to give you some points. So I would put those, if you're trying to draw the original graph, I would put those on there first. Because those are dots, you're going to have to go through them. And then it tells you, okay, at 2 and at negative 2, your slope is going to be 0. Hey, it gives you flat spots. Right? This is just reading and interpreting this to put it on your graph. Tells you your slope is going to be positive. Ooh, and they write it trickily like that. That sucks. So, right, when x is bigger than 2, your slope's going to be positive. And, tricking you, throwing the absolute value in there, if your x is negative 2 or less, so like negative 2, negative 3, right? You plug that in, that works. So at negative 2 or back, you're going to have a positive slope. And you're going to have a negative slope in between those. Concave down when x is to the left of 0, concave up when x is to the right of 0. Draw a picture that fits all of those conditions. 49, it's a piecewise, it's just like the example I did. It has you answer some questions. I don't think it asks for a graph. I'm asking for a graph also. So do all that stuff and graph the original, just for fun. So just those 4, those are the main 4. And then I want you to also do the multiple choice. These are not easy multiple choice. They're very difficult. They will take a lot of thinking. Some will take a lot of work to where you'll actually have to sit there and go through, like on 57, and do the derivative, and then do the second derivative, and then figure out what a needs to be. Like these are tricky. So give those a shot. So in writing, what that looks like. What section is this? I was going to do another video, but that's a lot. So, and this one was very long. Still haven't talked about position, acceleration, and velocity yet, but this is too much. So there it is. See you Monday.